I'll go and get started. If you haven't checked in yet, you still need to. Um, pretty much all the information in the discussion is was sent to you in your email earlier today. All right. So just as a recap, your test will be Monday. I will send out your test at 10 a.m. and it will be due at noon. Okay. And you have those 2 hours uh, to get the test, do the test, show all your work, take a picture of it, and submit it to on campus. All right. Uh, it should be plenty of time. All right. I did this last night, really taking my time and doing like four or five other things, and it took me about 15 minutes. Okay, so we should be okay to do it within 2 hours. The normal rule is like multiply by four. So if this were a normal class, I would kind of expect it to be done probably before the class to be actually finished. Okay, if you need more time, that's fine. You have it. Uh, it's it's there for you. Okay, um, but 2 hours is it should be enough. All right. Um, so I'm gonna go through this. I'm not gonna stop. Like I'll pause for a second between problems just so you can kind of copy it down if you need to, or check your answers. Um, but where you can ask questions is after this on Teams. So that's how this is gonna work. All right. So we'll just go ahead and get started on number one. All right. We have to see. So the directions here say to find the next three terms in each sequence. All right. So I'm actually probably going to change these directions just slightly on the actual test because it'll actually end up helping you out. And that will be to find the rule for the nth term. And then find the next three terms. That'll help you out just a little bit. All right. So if we just think about how we get from 1/2 to 2, 2 to 8, 8 to negative 32, and negative 32 to negative 128, we're actually multiplying by 4 a bunch of times. Okay, so and our first term is negative 1/2. All right, so our nth term is negative 1/2 times 4, and then we take that to the power of n minus 1. And I got this n minus 1 because we'd have to test the first term. All right, so if I plug in 1 here, 4 to the 0 is 1, and then we're left with negative 1/2. All right, 4 to the second, the second term would be 4 to the 2 minus 1, which is just 4. 4 times negative 2, or negative 1/2 is negative 2, and so on, right? So this equation checks out. And then we need to find the next three terms. So I'm not asking you to plug it in. Once you get this pattern that it's being multiplied by 4, you just have to keep multiplying the next term by 4, right? So the term after negative 128 is negative 128 times 4. Which is negative 512. Term after that is negative 512 times 4, which is negative 2048. And then the term after that is 8192. Okay, so we found the rule, and then we found the next three terms. Right. This next one is a little bit tricky, but if you look closely, or really if you take a step back and kind of look at each individual term, I noticed these two terms right here. And I noticed that this is the third term, and the numerator is 3. This is the fifth term, and the numerator is 5. And then I noticed that each of these are perfect squares. Okay, so then I thought, well, what if this 1/2, this actually could be 4/8. And this first one could actually be 2/2. And then this could be 1/1. Okay, so if we rewrote that sequence, we'd have 1/1, 2/2, 3/4, 4/8, and then 5/16. And then if we kept going, which would be the next three terms, right? It would be 16/32, sorry, 6/32, then 7/64, and then 8/128. Right, so all we're doing is increasing the numerator by 1 and then squaring the denominator. Okay, so our nth term rule would just be n in the numerator, right? Because the number of the term corresponds to the numerator term itself, right? So first term, second term, third term, fourth term, fifth term, and so on. And then the denominator is just powers of 2. Okay, so it's n sorry, it's just 2 to the power of n minus 1. All right, and again, we could check that. So this first term, this first denominator term, that's 2 to the power of 1 minus 1, which is 0. 2 to the power of 0, that's just 1. And then 1/1, that checks out for the first. The second term, we plug in 2 in there, we would get 2/2 to the 2 minus 1, which would be 2/2, and that checks out. And we could do that for the next couple of terms just to check. Okay, so I'll give people a second to just look at this, and then we'll move on. All right, then find the 10th term in each sequence. This is going to stay the same. For these, we just plug in 10 for n. Okay, so when you plug in 10 to both of those, for number 3 you get 102, and for number 4 you get negative 327,680. Okay, so this is just plugging in a number for n. Number 5, 6, 7, and 8 say to write the explicit formula for each sequence. What that means is to find the nth term. So we're trying to find an. And we need to see what's happening between 0, 4/3, 8/3, 4, 16/3, and so on, right? So if we just take all of those, if you step back and look at what each one has in common, you would see that most of them have a 3 in the denominator. And then between this second term and this third term, we're increasing by 4. Okay, so we know our nth term is going to have a denominator of 3. And if we rewrite these two terms that are just whole numbers, we could write 0 as 0 over 3, and 4, if our rule works out, should really be 12 over 3. So then we have to write a rule for the numerator in order to get from 0 to 4 to 8 to 12 and to 16. And you should notice that for all those numerators, we're just adding 4 to each term. Okay, so in order to get that, we would have to do, we can try 4n. Okay, so if we try 4n and plug in our first term, we should get 0. But if you plug in 1 into this formula, you're going to get 4/3. Okay, so then we have to modify it just a little bit to 4n minus 4. And then that's our rule. Number 6, again, if you kind of take a step back, you should notice that all the numerators are going to be 3, except for this middle one. And that's going to be like our problem. But again, if you look at it for a second, you notice that the denominators go 4, 5, and 7 and 8. So we could guess that this middle one is actually 3 over 6. And that should follow the pattern. Okay, so then for our nth term, 3 in the numerator is going to be a constant. And then we need a rule for the denominator. And you should notice that we start at 4, and then we're just adding 1 over and over again. Are these arithmetic or geometric sequences? Kind of. Like in number 5, the top is arithmetic. In number 6, the bottom is arithmetic. So there are pieces in there. I'm not telling you to define them like that, but if you want to look at them like that, you can. All right. So in the denominator, we need to start at 4 and then add 1 each time we go up a term. So that would just be 4 plus n, or sorry, 3 plus n. So if we test that, the first term should give us 4. So if we plug in 1 for n, we get 4 in the denominator. The second term should get us 5. If we plug in 2 into the denominator, we get 5, and so on. Okay, so a lot of this is taking a step back and just trying to figure out a pattern and then putting that into math terms. So then this is our nth term. Number 7. Number 7 is actually probably the one that probably the hardest on the test. Okay, but again, if you kind of take a step back and get rules for the numerator and get rules for the denominator, it will eventually come to you. All right. So I'm gonna take a couple of guesses here based off of what I see. All right, so I see 27 and 125. I know that 27 is 3 cubed, and I know that 125 is 5 cubed. And then in the numerators, 8 is 2 cubed, and 32 is 2 to the 5th. Okay, so there's some things that you should notice. On the 5th term, we're using 5 to the 3rd. On the 5th term, we're doing 2 to the 5th. On the 3rd term, we're doing 2 to the 3rd. And in the denominator, we're doing 3 to the 3rd. Okay, so that should give you a clue as to what each of these other numbers actually is. All right, so if that pattern proves correct, then we could actually write this sequence the middle one would be 4 cubed on bottom, and the top would be 2 to the 4th. The second term would be 2 squared, and the bottom would be 2 cubed. And then for the first term, it'd be 2 to the 1st over 1 cubed. And each of these checks out. 2 over 1 is just 2. 2 squared is 4. 2 cubed is 8. 4 over 8 is still 1/2. 2 to the 4th is 16. 4 cubed is 64. 16 over 64 is still 1/4. Okay, then we need a rule for it. So each of the numerators is some power of 2. That just corresponds to the number of the term, so it's 2 to the n. And then the denominator is the number of the term cubed. Again, that's probably the hardest that you would see. On number 8, again, we're going to kind of do the same thing. Okay, and the first thing that I notice is that each of these numbers are perfect cubes. Right, so 8 is 2 cubed, 27 is 3 cubed, 64 is 4 cubed, and 125 is 5 cubed. Which, if our guess is right, that would make this denominator 1 cubed. And then in the numerator, we're just going up by 2 each time. So the rule for the denominator is just going to be the number of the term cubed. The rule for the numerator is going to be the number of the term and then plus 2. And then that's our rule. And then you could go back and check that if you wanted to. I did, actually, and that's the rule. Okay, so these middle 4 probably the trickiest of the test, but as long as you kind of take a step back, get a rule for the numerator, get a rule for the denominator, and then put those things together, it should work out. Okay, for number 9 and 10, and even 11 and 12, for each sequence, state if it is arithmetic, geometric, or neither, then find the 10th term. All right. Arithmetic sequences are just adding a term over and over again, and adding a term over and over again is just multiplication. Okay, so I see multiplication here and nothing else, so this has to be arithmetic. Then we need to find the 10th term. So we plug in 10 and get an answer, which is 1774. For number 10, the number of the term is in the exponent. Oh yeah, sorry. This should be 2n plus 2. Or 2n minus 1. It should be 2n minus 1. Sorry. 2 times 1, that's 2. I did this wrong. I had this work up above. Hold on a second. I'll come back to that. I screwed that up a little bit. So we'll come back to that in a second. Actually, this is 2n plus 1. So you're right. The trick is getting what you know is happening into math terms. All right, so back to number 10. When your n is in the exponent, that means you're multiplying by something over and over again. And when that's the case, it is by definition geometric. Then we need to find the 10th term. When we do that, we get 59,049. On number 11, again, we have our n in the exponent, which means we're multiplying by something over and over again, which means that this is geometric. Then we need the 10th term. Three to the 9th is 19,683, and then there's that negative out front. You should know that if you want to take the negative to the exponent, this would have to be in parentheses, but it is not. So it just kind of stays outside. Number 12, we are multiplying by n, or sorry, we're adding over and over again. We're multiplying 20 by n, which means we're adding 20 over and over again. Okay, which means that this is arithmetic. And then the 10th term is 190. Number 13, show all, work, and evaluate each expression. There are kind of two parts to this. One is determining whether it is geometric or arithmetic, and then the second is plugging it into the correct equation. Okay, so this sequence is geometric, right? Our n is in our exponent, and it is finite because it stops at 12. Which means we are using the equation the first term times 1 minus r to the power of n divided by 1 minus r. Okay, so we need to find the first term, we need to find the common ratio. Common ratio is easy. That's just 0.3. And the first term is usually just this right here, this 4. Okay, so if we plug in all of those things, we get that s is equal to 4 times 1 minus our common ratio to the power of the number of times we're adding together, which in this case is just 12, over 1 minus our common ratio. When we plug that into a calculator, we get 1.428 and so on. For the second, for number 14, the first thing we need to do is just notice that this is arithmetic. Okay, so our equation for this, for the sum of an arithmetic series, is s is equal to the number of terms we're adding together divided by 2 times the first term that we're adding together plus the last term that we're adding together. Okay, so we need the number of the terms, the first term that we're adding, and the last term that we're adding. Okay, so the number of terms is the 6th term, the 7th term, the 8th term, all the way up to the 81st term. Okay, so the way I do this is 81 minus 6. That's 75. But that doesn't include the 6th term, so we actually have to add 1 to that. So the number of terms we're adding together is 76. The first term that we're adding is actually the 6th term in the sequence. So we plug in 6, and we get 14. And the nth term is the 81st term. Which is 164. And then we can plug all that into a calculator, into this equation. Right, so the sum is equal to 76 divided by 2 times 14 plus 164, and get an answer. So you should get 6764. Number 15, again, this is going to be geometric. Our n is in our exponent. And this is an infinite sequence, which means we're using the equation s is equal to the first term that we're adding over 1 minus the common ratio. So we need the first term, which is really the 5th term. which is negative 32 over 625. You can keep that as a decimal. So when you actually plug that into a calculator, you get 0.0512. That's fine. I just like fractions better, right? The next thing we need is the common ratio, r, which in this case is just negative 2/5. So then we plug both of these into a calculator, into this equation, and get an answer. So S is equal to negative 32 over 625 divided by 1 minus your common ratio, which is negative 2/5. So when we do that, get negative 32 over 875, or negative 0.03657. Number 16 says to find the sum of the infinite geometric sequence given the following. All right. I will say that on the test, I may not give that it's geometric. You may have to find that out yourself. Okay, but that should be pretty easy enough to do. Okay, again, the rules in the numerator, it goes 2 to 4 to 8 to 16. And then in the denominator, it goes 1, 3, 9, 27. Okay, the numerators are all doubling, so it's 2 to the nth power, right? First term is 2, 2 to the first. Second term is 4, 2 to the second. Third term is 8, 2 to the third, and so on, right? The bottom are powers of 3, but we need n minus 1 instead of just n. And actually, I probably will give you that as geometric, because this, you wouldn't be able to type that into a calculator. All right. But given that it's geometric, we can find the common ratio. Okay, so we would take the ratio of two sequential terms, what did I do there? Okay. This should be 4/3. So our common ratio is 2/3. Our first term is just 2, and we have an infinite sequence, which means our sum is the first term divided by 1 minus our common ratio, which is just 2 over 1 minus 2/3. When we plug that into a calculator, get 6. And then for the last 4, this is just an equation that we need to know. Okay, so 13 choose 6 is really 13 factorial over 13 minus 6 factorial times 6 factorial. And we need to be able to simplify that and get an answer. Okay, so this is equal to 13 factorial over 7 factorial times 6 factorial. which when we simplify this, we can do some canceling. And then when we multiply all the remaining numbers together, we will get $17, $16. Number 18 is very similar. Again, you just plug it into the formula. When we expand those, we can cancel out 1 to 20 in the numerator and 1 to 20 in the denominator. So we get 21 times 22 left over just 2 times 1 in the denominator. Which gets us 231. And then the same is true for each of 19 and 20. Okay, for number 13, I got 5.7. Yeah, I don't know why I put 1.42. That's what I got to. Okay. For number 18, 19, and 20, I did skip steps to get from here to here in 18, 19, and 20. But it's the same thing that's happening in this step in number 17. Okay, so it's expanding that factorial and then canceling out common terms. That's really the only thing I did different, just in order to save space and a little bit of time. Okay, so those are all the answers for the practice test. So I'm gonna kind of scroll through this quickly, just so if you have any like last second, like I didn't see this, you can go back very quickly. If you still didn't see something or want to go back, this will be up within like an hour, if that. Okay. And you can go back and kind of scroll through the video yourself. Okay. So I'm going to quickly go through this. And then after that, I'll start a meeting on Teams and you can ask more individual questions there. All right, so I'll leave this up for another 20 or so seconds. After that, in the next minute or so, I will start a meeting on Teams, and you can ask me questions there. I will close this and I will see you on Teams.